So I wanted to make a quick screencast and kind of explain some of the important concepts related to constant velocity motion. Okay. First, I'm going to take your lab results and I want to help you make them more general. Okay? So your lab results are very specific. Your lab results refer to this little toy car that went across the ground, right? So I want to make it general enough where you can use the same equations and graphs for any object that's moving with a constant velocity, right? Well, if you're moving with a constant velocity, your position symbol is x versus time graph has to be a straight line. That's what that slope right here is, your constant velocity. And in this case, you can see that your velocity isn't changing. So I'm going to refer to it as an average velocity. Okay? And if I zoom in on the graph, right, whenever I talk about the slope of a graph, I'm talking about a change that happens horizontally. This is a change in time in this case, because I have time on my horizontal axis. And there's also a change that's happening upwards in this case, because my slope is positive. So that's a change in position, right? So I'm going to get right. The triangle thing means change. So delta x refers to a change in position. Delta t refers to a change in time. And slopes in general are comparing a change in one thing with a change in another thing. So in this case, the comparison is between change in position which is divided by change in time. Okay, so we're defining the slope as our average velocity, and in your case, you said that the equation for this line was, let's see if I could do it. You said it was position, and I'm just going to make up numbers. Let's say 15 centimeters per 1 second times time, plus I'm just going to make up number like 3 centimeters. And you said that the 3 centimeters was the position at 0 seconds. And you said that the slope means that for every second, car moves 15 centimeters. Now, that's actually not an average velocity. If I add information about direction, in this case, I have a positive slope because I go to the right and I go up. If my graph had looked like that, it would be a negative slope. But my graph has a positive slope. So what I'm really talking about is for every second, the car isn't just moving 15 centimeters. It's actually moving 15 centimeters in the positive direction. Okay? So, in physics, this quantity here is called average velocity. Whoops. Right? And of course, after that, we have time. And at the end of our equation, we have the position at 0 seconds. Well, that's called our initial position. That's the name we give that. And then on the other side of the equation, that, to be more descriptive there, and to distinguish it from our position at the beginning, the position on the left side of the equation is position at any time we want. So I'm going to say at time t. Okay? So now we can introduce symbols. Okay? So in physics, for position, we always use the symbol x for position. So the beginning and the end, we have the symbol x. Now, because we're talking about position, and position is defined as how far you are from 0 position, and in what direction are you from 0 position, right? So position is a vector quantity. It has information about how far, it has an amount, that's a magnitude, but it also has a direction. So when you get information about direction as well as magnitude, you're talking about a vector. And that's what these symbols mean. I'm just reminding myself that those are vector quantities. They're not just numbers. And to clarify with subscripts, my position at time t, I could put a little tiny t there to remind myself that's position at any time t. And my initial position is actually at 0 seconds. So I can put a little 0 there. Okay? And then I would put my plus. And then the symbol for time is just t. Okay? The symbol for average velocity is just a v with an AV by it. And this is our equation. This is a super useful equation in symbolic form. Okay? And that equation would only be useful if we had constant velocity motion. Right? Now, unlike a position time graph, we can also draw a different kind of graph. Okay? Position versus time is where you're at every moment in time. But we could also draw a velocity versus time, which is something totally different. Velocity is how you are moving. It's precisely describing the direction you're moving, and it's describing how fast you're moving. So no longer are we talking about a where you are located graph. We're talking about a how you're moving graph. And if you look carefully, the slope on your position graph, the slope on your where you're at graph tells you how you're moving. You can see that that slope on our position time graph isn't changing. It's a constant slope, meaning that we have a constant velocity. So when you draw your velocity graph, your velocity isn't changing. If I want it to correspond, I might have a value of 15 centimeters per second, and I just have a nice horizontal line, right? And time would be measured in seconds. And I asked you today to come up with an idea of what this area represents, because this ends up being very useful for us in physics. And so the area of our velocity graphs, right? So, all right, area of velocity versus time graph, right? The area of a velocity versus time graph is going to be measured in centimeters, You can see that because you're multiplying centimeters per second times seconds, right? It's measured in centimeters. And in general, while a slope describes a change in one thing compared to or divided by a change in another thing, areas of graphs show us just a change in something. So velocity graph here is showing us a change in something that's measured in centimeters because a rectangle, right? And the units of that rectangle are centimeters. So it's a change in something measured in centimeters. It's got to be a change in position, right? And recall also that a velocity graph can't tell you where you're at, but it can tell you how where you're at is changing. That's what this area is doing. In other words, this area is giving you a change in position. And the symbol for that would be change in, that's what the triangle means, and the X means position. Now, to calculate a change in position, you would find the final position at time t minus the position at time 0. Now, since you're subtracting vectors to get your change in position is also a vector. And it's given a name in physics. So this change in position is called something. It's called displacement. And there you go. So again, displacement is your change in position. It's the area of your velocity time graph. And I can actually take our equation in general, and I can even show this to you another way very briefly. Okay? So I'm going to take our general equation for the position of an object at time t, which is v average times t plus my initial position, right? I can subtract initial position from both sides of this equation, right? Let me draw it a little bit further below. So I'm going to subtract my initial position from both sides. Okay? Now on the left side of this equation, I get final position at time t minus initial position at time 0. And that has to equal velocity average times t, right? Now, this final position minus beginning position, we already said that's my change in position, right? And since I'm subtracting vectors, I must get a vector. I don't just lose information about direction. But I can't just subtract vectors the way I subtract numbers. I'll show you that another time. But I got V average. Let me go back a little bit. V average T, right? So if you look carefully at this, you should be able to make a connection with, oh my gosh, this area would be calculated by multiplying V times T. And that's our displacement, which is our change in position. So all these equations are actually connected. They're all representing the same thing, these equations and these graphs. And these are our primary tools for solving problems in physics. We would typically use the graphs to figure everything out. So I would encourage you not to try to memorize anything. I don't think that will help you. But when you're given a situation, immediately try to sketch the graphs. And that should definitely help you out. Anyway, I hope that helped. And have a good day. Thank you.